Okay, so the title of my talk is Scalable Bayesian Inference, New Tools for New Challenges. And that kind of summarizes also kind of my research agenda. So the research in my group will be kind of all be done under this common umbrella of Scalable Bayesian Inference, and I'll show some examples of this. And then there will be two parts of that. One will be I'll be developing new tools, kind of foundational research on models and algorithms. And these, my goal is that these tools allow us to address not only to address existing problems in a better way, but actually to tackle new challenges that weren't possible to haven't been addressed by machine learning so far. And then these new application domains have introduced some feedback loop in that they guide the research on foundational research, and they also provide new evaluation metrics, and we'll see some examples of that in the talk. Okay, this is pretty abstract, so let me start actually with a very concrete example. And the example here is I want to show a model that allows us to capture or to investigate how language evolved over time. So for example, the word computer used to be a job description, and now it obviously refers to an electronic device. And this kind of question of tracking the evolution of language is, I think, something that a lot of people are interested in. So, for example, just this weekend, the Süddeutsche Zeitung, one of the one of the largest German newspapers, had this article where they analyzed corporate language over the past 30 years. But usually these kind of tools are very kind of simplistic in the sense that they just count frequencies of how frequent certain words appear, but that doesn't allow you really to capture, the changes of word meanings. So to capture that, we built a probabilistic model, and this is kind of the result of this, one of the results of our model. So these are the 10 words that in the English language that our model thinks have changed the most over the past 1.5 centuries. So the way to, there's no cherry picking here. The words are really the 10 top words, and then the way to read each of these panels is you always have a central word. So for example, here the word peer, and then in red you see the kind of 5 words that were considered most, that the model considers most similar to the word peer in the year 1850. And then the blue words are kind of the modern synonyms. And you can see, for example, here there's a crossover. You may recall that the British upper house is still called the House of Peers. That's why it used to be considered similar to nobleman and lawyer and knight. But now it has gained a different meaning. And you can do this even kind of dive even deeper. So here in this video, for example, you see a lot of points. Each point corresponds to a word, and we see I highlighted the word broadcast in red, and it's kind of 5 nearest neighbors in orange. And you can see at the beginning of the 20th century, broadcast had kind of a very generic meaning, kind of agricultural also. And then in the 30s, if you look here, word broadcast suddenly moves to a new location in this semantic space. That's exactly when the first commercial radio stations were established. Okay, so how did we do this? And so for this introduction, I will kind of give a brief introduction into probabilistic models and scalable inference. I know that this will be a repetition for a lot of people in this talk, but I'll try to give it kind of a new twist and to highlight an aspect that I think is often overlooked. Okay, so we weren't the first people, who analyzed the evolution of language. And so the way that people have done this in the past is, they looked at, historic books, and then binned them, for example, into years. And then for each year, you would train some machine learning model that fits so-called word embeddings. So these point clouds where kind of each word corresponds to a point, and then nearby points represent similar words. And then you would do that just for every year or every decade, or depending on how precise you want to be in time. And then the idea would be that you can now track how these point clouds change over time. But this is actually this will actually not work very well. And the reason why there's a problem is that you have to align these embedding spaces. And that turns out to be more difficult than you might think, because you're really looking for very subtle signals. Most words don't change their meaning. Only very few words change their meaning. And you have a lot of noise. Should read noise in the caption with an E at the end. For example, if you use this naive method and you fit, word embeddings for the year 1998, and then you did the same for the next year, 1999, this is what you would get. And here, these colored lines correspond. They show how these word embeddings have moved over time. And this is already using some techniques that were around in the literature to try to align these embedding spaces. But you still see, it's hard to find anything interpretable in this kind of chaotic representation. So the way we address this is, or first let me show you what our model can do. So in our model, you get this picture where most words, most word embeddings don't change, so they stay where they were, as you would expect, and then only few words change their position in the semantic space. The way we did this is we used a probabilistic time series model as a prior, and then combined this with a scalable approximate Bayesian inference method, and also it turned out that we had to develop a specific kind of advanced optimization algorithm because of some symmetry issues. I won't get into the details of this last point, but I'll kind of explain what I mean with probabilistic time series model and a scalable approximate inference. So what we did is we started from the other way around. So we started, from these word embeddings, and we posed a probabilistic time series model that kind of just states how these point clouds can evolve over time, just in general, in a probabilistic way. It's kind of a diffusion process. And then given these point clouds, we pose what's called a probabilistic generative model that then is kind of a model of how, starting from these point clouds, you would kind of make up a hypothetical process, a very simplistic hypothetical process, how you could write books based on these point clouds. And you do this again for every year. And of course, this probabilistic generative model is extremely simplistic. You would not get like realistic books, but it's good enough to capture kind of the main semantics of words. So with this, you have kind of a probabilistic models over books, over more than a decade, and now you can look at actual data and actual digitized books, and then you can invert this model, and this inversion is called inference. So how does this inference work? Well, we do probabilistic inference. So we start from a probabilistic model, which is a probability distribution over observed data, which I'm going to call X. In our case, this was the digitized books, and then latent variables C, which in our case were these point clouds that represent words. And this is usually the product of what's called the prior. So that in our case, that would be this time series model, but it could this diffusion process, but it could also be a scientific model, and then a likelihood, which in our case was this this natural language model that describes how books can be generated from, or hypothetical books could be generated from these point clouds. And then the task of inference is to turn it around, so to get the so-called posterior, which is the probability distribution of these latent variables C, given empirically observed books X. And you can write down a formula for this posterior just from probability theory, Bayes theorem. But it turns out in practice, you won't be able to actually evaluate this. And the reason why you won't be able to do this is because this denominator, this integral in this denominator is typically, for large models or, non-specialized models is typically intractable. Or at least that's what, in these talks about, scalable Bayesian inference, you would usually hear. that this denominator is really intractable, and that's why you need to introduce some approximations. And that's not wrong, but I think this statement is kind of misses an important point. So let's assume you were able to evaluate this normalization constant. It's just one single scalar. Let's say you had some oracle that would tell you the value of this scalar, of this denominator. I would argue even if you had this value, it wouldn't really buy you a lot, because then the exact posterior, which you always think you're looking for, this exact posterior would typically have thousands or even millions of terms, because it's typically like one term per data point. So in a big data regime, you have really a huge equation that just you could in principle write down the exact posterior, but it would be a huge equation, and so it's not really clear to me what would that buy you. So my claim is that in many practical applications, especially in these deep probabilistic models or big data regimes, you don't really actually want to get the exact posterior. What you want instead is you want to get a scalable method, so one that scales to large models and large data sets, and that provides some compact approximate posterior. And there are a lot of different methods out there that do this. I'm not going to go through all of these. I'm just going to highlight that all of these methods, they give you a different kind of compact representation with different approximations and therefore different trade-offs. So you might be asking yourself, which of these approximations works best? And as you could imagine, the answer is a resounding, well, it depends. Right? So more precisely, it really depends on the task that you want to solve, and more precisely the constraints of the task, because it's always a trade-off between computational cost and then approximation gap that you get from these approximations. And for different applications, you might different aspects of the exact posterior may be more important than for others. So this is kind of the main claim of, brings me kind of to the main claim of my talk. So the claim here is that, whether a certain approximation, in our case of the exact posterior, is good or bad, that really depends on the constraints of the application. And therefore, I would argue that, if you do foundational research on, inference methods and scalable Bayesian inference methods, it should always be guided by some, concrete applications, ideally some resource constraint applications, so that you have to make these trade-offs in a very thoughtful manner. And that's exactly what my research interests are, kind of in more detail. So I'm doing research on scalable Bayesian inference methods, but then also so this is kind of foundational research on kind of generic methods, but I'll also always apply them to different resource constraint applications. And in this talk, I'll focus on, I'll show you one example of a new inference algorithm that we developed, and then I'll show you two examples of kind of new and emerging application areas where these inference algorithms really allow us to tackle new problems. So let me start with this new inference algorithm. And this was a collaboration between Zhong Zhang, Manfred Opper, and Stefan Mand. But actually, before I go into this, are there any questions so far?
I don't have any in the chat, Robert. So
okay.
just continue.
Yeah. Okay. By the way, I'm leaving the chat open next to it, so feel free to type something in there. I'll try to address it. Okay. So this was a new. This paper was a new scalable inference method that we developed. But before I go to the specific method that we developed, let me introduce kind of the general kind of framework of methods in which this falls, and that's called variational inference. So remember, we want to find this, what I defined as the posterior distribution, or some approximation of this posterior distribution. And it's typically a very complicated function, and we can't really find it exactly, but we know that it's some function over, or like some probability distribution over all latent variables. So it's somewhere within the space of all possible probability distribution. And then what variational inference does, it poses some subset, a so-called variational family of probability distributions that you can parameterize efficiently. And then you take some initial candidate and you minimize a distance between this candidate and the true posterior. This is kind of a very simplistic picture, but you can already see, in the simplistic picture in this, general framework, there are a lot of things that you could improve. So for example, you could make this variation family larger, and we did some work here for time series models. You could make this optimization problem faster, and this actually turned out to be a problem in these dynamic word embeddings that I showed you earlier. Or it's also not really clear what this distance measure should be. And this is what I'll be focusing on in the next 10 minutes of this talk. So we propose here kind of better distance measure that kind of gives you a better approximation that, if you minimize this new distance measure, you get a better approximation of the true posterior. Okay, here's just on one slide very briefly the idea, and then I'll go in, after this slide, I'll go into more details. So remember, we want to, in order to get the true posterior, we need this normalization constant, this integral over all the latent variables C. We can, which is usually intractable. So what standard variational inference, what I just showed you on the last slide, what that usually does, it poses a lower bound on this on the logarithm of this constant, and this lower bound depends on Q, which has some parameters, some free parameters that you can vary. And so you can just, since it's a lower bound, you can just vary these parameters to maximize this lower bound. So since it's a lower bound, if you maximize it, it will become as close as possible to the left-hand side. Now, our observation is that this lower bound that's usually used is actually very similar to what's called a perturbation theory in theoretical physics. So there's a popular perturbation theory that's called cumulant expansion. And in this perturbation theory, you can kind of write this, this left-hand side as the first term here is minus v is just the term that's in the bracket, so nothing changed here. But then this perturbation theory allows you to actually improve on this. Let me see. Yeah, so to add additional terms to this, it's kind of an infinite series that has additional terms of growing complexity, and each term kind of brings you closer to the true value. Now, I don't expect you to remember all of these terms. In fact, even for physicists, these become too complicated at some point, so that they invent kind of a pictorial representation for these terms. And these perturbation theories are so popular that these pictorial representations even made it into pop culture. So this is still from the Big Bang Theory, for example. Every one of these doodles on Sheldon's whiteboard really corresponds to one of these terms in the cumulant expansion. So this is a very popular method in physics, but it has a problem for machine learning. That is that it's really now just an approximation, but no longer guaranteed to be a lower bound. So we can no longer just maximize the right-hand side, because it would typically diverge, because there's no guarantee that it will stay lower than the left-hand side. Scalable. I'll answer the question in a second. In this paper, we kind of came up with something similar, also perturbation theory, but kind of a new kind of perturbation theory where you can prove that if you do it to odd order, it will always stay a lower bound. No, there was a question: can you scalable tractable probabilistic circuits as they allow you to calculate normalization constants in linear time? Right. So there was a question, if I understand it correctly, in specific models, you can do kind of inference or probabilistic inference in efficiently. That usually requires you, that would be a different method, but that usually requires you to that limits the kind of models that you can use. What these methods, variational inference, and also the method that I'm proposing here, the advantage of these methods is they're called so-called black there are so-called black box methods, which means that they can work on pretty much any model, except if you have maybe like implicitly defined models, but otherwise pretty much any model. So they can also work with, models that are parameterized by deep neural networks and things like that. That's very attractive. Okay, so this is kind of the overview of our method. Now let me go. I hope that it kind of gives you the rough idea, but kind of some things may appear magical. How did we come up with this equation on the bottom? So let me go become a bit more detailed. So again, we want to evaluate this integral, which is typically intractable. So one thing I can do is I can introduce just a new probability distribution, and I can multiply it by it and divide by it. Nothing really happens. But now I can interpret this as kind of sampling. So this E is short for expectation value, as sampling from this probability distribution. And here phi are some parameters of this auxiliary probability distribution Q. So this method is called importance sampling, and it's really an exact equality. So there's no approximation here. But the downside is that it usually doesn't work in high dimensions because the variance of samples that you could draw from this term in the brackets, from this importance weight, the variance typically scales exponentially with the size of your model. So for a large model, the samples would have extremely high variance, so estimating the expectation value would become extremely hard. So what variational inference does, it introduces a bias, which on the other hand then allows you to reduce the variance. And the way this works is we look now at the logarithm of this constant, and we again write this constant as through importance sampling. But now we pull the log inside the expectation. And that's obviously no longer an equation, but it turns out this leads to an inequality, which is called Jensen's inequality. And now, so due to this inequality, now have a bias, so it's no longer an equality. But if you take the log of some highly oscillating function, then now the samples here are much more well behaved. They have much lower variance, so you can estimate also the gradients of this term in a much better way. And this lower bound is called the elbow or evidence lower bound. So our question was, can we make this bound tighter? So let's look at this equation again. And so now it turns out that here we're pulling the log inside the expectation, but it turns out this inequality holds not only for the logarithm, but for any concave function. And you can kind of, to kind of give you a pictorial reason why this is the case, let's call this importance weight psi, and then let's assume that instead of the logarithm, we had a linear function. So what we're doing on the left-hand side is we're taking a lot of these samples from psi, and we're taking immediately the expectation of these samples, and then we're applying, in the real case, we're applying the logarithm, but now let's assume just that we're applying a linear function. And by contrast, what we do in the right-hand side is we take all these samples, we map them directly, and only then we sample. So it's easy to convince yourself that for a linear function, it doesn't matter which order you do it as. But if you have a concave function, then on the left-hand side, nothing changes. But on the right-hand side, the higher the variance, the broader these samples deviate from each other, the more you will get, the lower your final value will become. And this holds not just for the logarithm, but for any concave function, so any function that has kind of a right turn. So this means that we can kind of generalize this bound. So instead of the logarithm, we can now pull in any function f as long as it's concave. So on the left-hand side, again, we have importance sampling, and then on the right-hand side, we have some biased importance sampling, but on the advantage is that it has lower variance if you choose f conveniently. So we can kind of make this trade-off between, small bias and high variance, where at the extreme case, if f is the identity, then we just have importance sampling. Or on the other extreme case, if we have like a large bias but low variance, then we can do standard variational inference where f is the logarithm. but now by choosing different f's, we can tune different points on this trade-off. For example, we identified that a previously a proposed method called alpha variational inference can be identified with a different a kind of function f. But now the question is, how should we choose this function f ideally? And here our idea was that, since the samples psi, they kind of scale exponentially with the size of the model, typically, we want to make f only depend kind of in a polynomial way on the logarithm of psi, so that they are kind of well behaved, are don't show too much variance. But at the same time, we want to be f similar to the identity function so that the bias is not too large. So how can we do this? We can again write this, importance sampling. And now I rewrote this kind of in a peculiar way, where I introduced V, which kind of has the interpretation of an interaction energy, which is kind of the log of this, inverse of this ratio. And nothing really happened here. I just pulled out a constant V naught, which can be any constant. And then I also introduced a parameter beta, which I set to to 1 in the end. So you can just think of it not existing here. So why am I writing this in this complicated way? Well, because this is still an exact equality, but now I can make a Taylor expansion in beta, and that by making a Taylor expansion in beta, I kind of keep track of how many orders of V I include in this expansion, and this leads to actually kind of a whole family of approximations to this left-hand side. And we can show, first of all, we can show that the kind of 0th order of this, actually the first order of this expansion is exactly the elbow that we had before. So we can kind of recover the method that we already know. But then higher order terms are kind of correction terms that get you closer to the true result, so that they reduce the bias. But we can also show, interestingly, that if you stop this expansion at any odd order, it turns out it's actually a lower bound. We prove this in our paper. Okay, so let me conclude this part with some results. So first of all, we see that this new bound is tighter due to these correction terms. Here is an example. So again, this is the function f, so that you get out of this construction. So again, black is kind of the identity function, so that would be importance sampling. Pink is the logarithm, so that would be standard variational inference. And then green is kind of the first if you take our method to the first non-trivial order, and then you can take it even closer and closer, and so even to higher and higher orders, and will become closer and closer to the importance sampling case. So we're kind of, again, making this trade-off between small bias, high variance, and, bias and variance. And, due to this, well-behavedness, because it only depends on the logarithm, we can show that gradient noise is much lower. So our method is the green method here. I'm plotting here average variance of the gradient, which is kind of very important quantity. If you want to optimize something numerically, you need a low variance of the gradients. And you can also actually see this in experiments that our method converges much faster than existing competing methods that have much higher gradient noise. And we see that our method is kind of not as prone to to kind of underestimating posterior uncertainties. Maybe this is something more for experts. Variational inference is known to underestimate posterior uncertainties. Our method is kind of less prone to this, both in toy experiments as well as kind of some more like real life experiments. But more importantly, our method not only allows us not only to do better inference, but actually more directly, it allows us to estimate this normalization constant, its marginal evidence better. And this is actually a very important quantity that you want to optimize in the so-called variational expectation maximization algorithm, which has become popular in the recent years due to its application in variational autoencoders. And we see that with our method, we can get better predictive performances, especially if we're training on, if we don't have a lot of training data. Okay, so this was kind of the most technical part of my talk. Before I move over to the next parts, again, are there any, oh, there, I see a couple of questions. Will Q still be an approximate posterior under different F? Yes, in general, it will be as long as F is not the identity function. If F is the identity function, then Q can kind of be anything, and there's really no force for Q to become, the approximate posterior. But you can see if you go back to kind of this picture, the more, here, if you have this concave function, if you have any concave function, the broader your samples are spread out, the more you can see the effect of this bias due to the concave function. So you will, by maximizing this term, you will make sure that these terms don't spread too much, and you can see that will force Q to become close to the true posterior. And it's we'll leave the tail experiment. Could you give some intuition about we should choose this value? Oh, right. That was something okay, so then the next question was this value V naught. How do we choose this value? So I forgot to mention this. So this value is an arbitrary number, and this bound is really a lower bound for any V naught, so we can just maximize over it. So maximize this bound over both the parameters of Q as well as V naught. So we get the optimal value just by maximizing. Okay. Okay, so this was the most technical part, and this kind of concludes, I showed you kind of a new method for scalable Bayesian inference. Now turn over to the first application, and that's, or kind of an emerging domain of application, that's neural compression. There's actually already been a lot of work also here in Tübingen on neural compression, but I think it's still a very kind of new field where there's a lot of progress and a lot of open questions still. So I'll show here two papers that I did in collaboration with a very talented student, Ivo Yang, and my former supervisor, Stefan Land. So I think neural compression is becoming really interesting. First of all, for two reasons. First of all, we have a lot of, data that's transmitted every time that needs to be compressed. For example, the Zoom call needs to be compressed in a very efficient way. And we're just at the word where neural methods start to outperform existing methods. But then the other reason is that these compression methods for video and audio, they have had a very long history, and that a lot of money has already been invested into tuning existing non-machine learning based methods to get high performing compression methods. But there are a lot of data sets out there that have much more obscure types, especially in sciences, where you have data sets, huge data sets, but of very peculiar types that would benefit a lot from compression, but where the kind of business, where there's not really a business case for investing decades of research into manually fine-tuning compression algorithms. And I think machine learning can really help here by automating a lot of this process of coming up with a new compression algorithm. Let me first start kind of with a simple example, a compression algorithm that we developed for images and we published recently. And I'm showing this mainly to introduce kind of this metric, this the kind of a new metric that I think is very interesting for Bayesian inference, that's called rate distortion performance. So what you see here on the horizontal axis is we tune through different, we compress images with our method and with other competing methods, and we tune through different qualities of reconstruction. So we compress them in a lossy way, and we set different quality levels. And then on the y-axis, you see, how you typically measure, how many bits do you need to store an image, to compress an image to this quality. To make it, better readable, what I'm actually showing here is I'm showing the relative rate savings compared to the best existing classical method. So in this case, higher would be better because, it means that we save more bits compared to the classical methods. So the purple line, kind of the 0 line, is kind of the best existing classical method. And there are already now been machine learning methods that outperform this classical method pretty significantly, but they are extremely expensive, so computationally. So in this paper, we kind of started from a cheaper, a computationally simple, cheaper model. And so instead of now tuning this model, we kept the model pretty much as it was and only changed the inference method. And just by changing, improving the inference method, we get much higher savings in terms of bitrate. So we can compress to much smaller files. And actually, if we now change the models just slightly, we can actually use a different entropy, so a different compression method, different compression algorithm that allows us to save just a little bit even more. So I'm not going to go into details of this specific compression algorithm. All I want to kind of highlight here is that in this area, there's now really, modeling, inference, and then also compression, so entropy coding, as it's called in the information theory literature or signal processing literature. These three things, modeling, inference, and entropy coding, they really go in lockstep. And different models allow you to do different inference algorithms, and these again allow you to employ different entropy coding algorithms. So it's really a very interesting interplay between models and algorithms. Okay, so more generally, so what can we do with neural compression? So we can apply this for two things. We can do data compression. That's what I just showed you, and this is usually uses an autoencoder architecture where you have some small intermediate representation that you then entropy code. But you can also compress models. So in a lot of cases, you have a model that you train on some data. For example, our favorite word embedding example, where you train it on a lot of digitized books. But then once you've trained it, you don't really care about this training data anymore, and you only care about the model. And we can also apply, model compression, these compression methods there to store these models or transmit these models in an efficient way. Okay, and so why? And so, yeah, so the general way that these, compression methods work is that kind of follows the slogan, don't transmit what you can predict. What this means is that in order to compress data, you need to have a very good generative probabilistic model of the data. In fact, you can show that the optimal kind of expected bit rate that you get is given by the cross entropy between the data and your model, and which is typically what we kind of minimize anyway in machine learning. So better probabilistic models allow you to, at least in theory, to develop better compression algorithms, and that's why probabilistic models are really important here. I'm just going to show you one one example of such an entropy coding algorithm that employs a probabilistic model, because then this is kind of a classical example, but the method that our method that I'll present later will kind of build on this. So let's say you want to transmit a message that's a number from 0 to 10, and it follows this, a plotted probability distribution. So what arithmetic coding does, it first kind of, at least, in conceptually, you draw out the cumulative probability distribution function. So here, every orange bar kind of has the same height as the corresponding blue bar in the same column, but they're kind of stacked on top of each other so that they go from 0 to 1 because, probabilities sum up to 1. And then let's say you want to transmit the number 7. What do? You look up this, the cumulative density function for the message 7. And then you can identify this kind of bin by any number on the vertical axis that's kind of in this bin. So which number do you choose? Well, you write out all the possible numbers kind of in binary, and you choose the number that's within this bin, but that has the shortest binary representation. This may seem like kind of a funny, algorithm, but you can actually prove that this is the information theoretically optimal way to compress data. Okay, so this is why probabilistic models are important for compression. Now, one new thing that we showed is that not only probabilistic models, but also probabilistic inference is important. And this is because we found, and this can be kind of summarized in the slogan, don't transmit what you're not sure about. So that means you need good posterior uncertainty estimates. And you can kind of easily see this with this kind of toy example. Let's say I ask you, what is the population of Rome? So if you look this up on Wikipedia, you would find this very kind of specific number from the last census, which was 2,879,728. But if you dig deeper into the article, you would find that in the year 500 AD, the population was about 100,000. So you see that, for this, 500 AD, Wikipedia gives you a much more gives you a rounded number only. And the reason for that is because, historians are just not that sure about this number. So if you're unsure about something, we should represent, it's kind of natural to us humans to, to represent these numbers kind of with lower accuracy. And that's exactly how our method works. So here's, this is kind of a new compression method that we developed that uses Bayesian inference to exploit posterior uncertainty estimates due to Bayesian inference to increase compression performance. So here's an example, kind of a toy example. Let's say you want to, your model is kind of a linear regression. So you have these gray data points and you want to fit a line through it. Now this line can be represented by, a slope and an offset. So you can, plot slope and offset on the X and Y axis of this diagram. And so your model would be just a point here. Now, typically, if you want to compress this model, in order to compress, you need discrete parameters. So you would kind of introduce some lattice in the space and then round to the nearest lattice point. And that obviously, on the left-hand side leads to some, some mismatch in the model. Now, what we observed is, what we argue is that, we don't only know, the model, we also know the uncertainties of the parameters. So we have like a full posterior probability distribution in the latent space. And now what we can do is we can introduce kind of a new grid. The main point of this paper was, to argue how, the optimal way is to introduce this grid, and that exactly builds on this arithmetic coding idea that I showed you earlier. Where in this grid, it's kind of a dense grid, so I'm showing you only a subset, but different grid points cost different amounts of bits. So you can now make this trade-off that's saying, okay, in one direction, in the B direction, I don't need to be that precise because I'm kind of uncertain about it anyway. So I'm willing to be kind of off here, but on the A direction, I want to be very precise and I'm willing to pay one more bit. And yeah, with this, you can get, on the left-hand side, you get much better, a better approximation of the model. Okay, so you can use this for data compression. So for example, for images, if you take this image, you can compress it with JPEG, and this in comparison would be our model. So again, this is JPEG, this is ours. But you can also use it for model compression. So for example, here's our favorite word embeddings. If you compress this, and on the y-axis here, I'm showing some measure of model performance, and you see if you reduce the number of bits in your model, performance drops. But with our compression method, you retain much higher performance at lower file size. And we can even scale this up to our dynamic word embedding models. And I'm not going to show you go much deeper into that, but I encourage you to look at this website where we used our compression algorithm so that we can actually run this model. So this compression algorithm allowed us to make this model small enough that it can actually run in your browser. Because it can be downloaded pretty quickly, and then you can interact with it extremely quickly because it runs directly on your machine. You don't need to make any server calls for every interaction. Okay, so this was the part about neural compression. I would like to very briefly, just in 3 minutes or so, talk about other application, which is more of an outlook, because I haven't published any work here yet, so I would usually not display such an outlook in a colloquium talk. But I was kind of prompted by recent political events because I think this is becoming more and more important. I want to kind of advertise this new direction of research. And the recent political event is shown here. So I'm sure you've heard that, Twitter banned, and a lot of other platforms banned Donald Trump from their platforms recently. And I mean, there's been a lot of praise for that, but also a lot of criticism. And, no matter, which side you are on this debate, I think one thing that we can all agree on here is it's really problematic that we were in the situation in the first place. So it's really problematic that, a handful of, huge corporations have the power and also, the obligation to judge what's true and what's not true. And I think this is a statement that, not only both sides of the debate, but even, the CEOs of these companies would agree on, would assume, Facebook and Twitter, they don't actually want to have this responsibility, having to judge what's true and what isn't. And I think this is really becoming an increasing problem in the software service industry. And I think that machine learning is actually accelerating this problem because, most machine learning services right now work kind of as a centralized service that collect data and then give you, model predictions. And that leads to kind of a feedback loop where, if you have a large service, then you have more users, so you can train, collect more data, so you can train better models, and that allows you to provide better, services that attract even more users. And I think this is really problematic. And I'm kind of working towards kind of a decentralized version of that. So just kind of as a disclaimer, when I say decentralized, I'm not talking about federated learning. So federated learning is where, you have kind of different, delocalized data centers that all learn kind of parts of the model, and then they interact with some, main hub that kind of keeps, orchestrates all the learning process. But that's, in my opinion, still, centralized in two ways. First of all, usually, all these data centers are still controlled by the same institution, so they may be decentralized in a geographical sense, but not in an institutional sense. And then also you still need, so this is kind of due to, this centralization is kind of due to the business model that, because there's otherwise, for true institutional federation, there's not really a business model yet. And then, but there's also a technical limitation that you still need this authority, this kind of central authority, to come to a consensus for the trained model. Okay, and my goal is kind of to overcome both of these limitations. And kind of the vision here is to have kind of a model as a shared data structure, and then to keep where kind of each user keeps track of a partial view of the model. And these partial views, I mean, are kind of oriented about, what's relevant to each user, but they're obviously strongly correlated. Because that's the reason why, why it makes even sense to combine these, data points from different users, because users may have different, similar preferences, and, these correlations allow you to reason about preferences of one user given preferences of another. And by modeling these kind of correlations explicitly, we can reach something, we don't have to, share the entire model. We can reach something that's, I would term as lazy consensus by, reaching consensus only when we actually need it. But we still have to kind of overcome this, this way. How do we actually reach consensus, and how can we build a business model around that? And I think there's a really interesting recent development in the area of blockchain technology, which are basically technologies that allow you to reach consensus without a central authority. So my vision here is that we are building kind of an experimentation platform for machine learning, for a kind of a new kind of decentralized machine learning on a blockchain. And I can point you to kind of a minimal viable product that I implemented on this, if you can read the link. And the idea here is that this is really a kind of new kind of machine learning that it really makes sense to first develop a platform so that, both we, but also other researchers can more easily then develop kind of new machine learning algorithms on that. And this is such a kind of new kind of deployment strategy that it opens up a whole array of new research questions, starting from security to, how do you actually build a business model around this, that I think would, be extremely interesting to explore. Okay, with this, I would like to sum up, and I would like to thank you for your attention, and I'm looking forward to a few more questions.